Okay, so today I will talk about Nature.mtl paper. It is called Distance-Dependent Magnetic Resonance Tuning as a Versatile MRI Sensing Platform for Biological Target. The author actually proposed one method to use MRI to detect some molecular events. So he called this method MRET, MR tuning. So actually, these authors are chemists, so they study some uh, like a T1 relaxation agent like gadolinium DOTA, and they also investigate some T2 enhancer, T2 relaxation enhancer. That is like the 12-inch, not 12 nanometer uh, nanoparticle. That one here is a T2 enhancer. And they find if you put the T1 and T2 together, and the T2 nanoparticle actually can decrease the gadolinium's T1 relaxation ability. That means they explain like this. Uh, the closer you put the gadolinium to the quencher, and the quencher actually can repel the water, the bonded water. So the gadolinium do not have so many bonded water, or the bonded water, the correlation time is lower, so the Z direction relaxation uh, is decreased. That means it will take a longer time to recover the Z direction magnetization. With this effect, and he found it is very interesting because here is one result you can see. If you put the quencher and the enhancer we call enhancer E and quencher Q, if you put the Q and E quite close and there is no T1 signal, if you put it quite far away, the T1 image is quite bright. Uh, that is, if you put it far away and there are more bonded water around the gadolinium, and the gadolinium can relax the T1 very fast. That means the relaxivity coefficient in Z direction is bigger, and in that case, and it recover the Z direction magnetization very fast, and then from the T1 image you will see it is quite bright. So with the Q and the E, and we can do some quite a lot of other things. Uh, this is very important discovery, and so the author gives some examples. Like here, you can see, uh, as we know, the sulfonate bond, this is sulfonate bond, the O and the S, they have a bond in between. And this bond, if you have some, put it into the H2O2 condition, and this bond will be broken. So if you bind the Q and the E to the molecule that contain the sulfonate bond, and if there is no H2O2, and the Q and E are quite close to each other, and from T1 image there's no signal. But if you put some H2O2 in, and this sulfonate bond will be broken into two parts, and then the Q and the E, they are the distance are larger than the critical distance, that is 7 nanometer. So the gadolinium can take its role to do the T1 relax. So the T1 image is bright. And the same thing for MMP2. Later we will talk about this in detail. And then for binding, and if you bind the Q to the azide group, and you bind the other, the E enhancer, to the alkene group, and these two groups actually can combine together in condition of copper ion. So if there is no copper ion, and the Q and E are quite far away to each other, and you will see T1 image is bright. But if you add some copper ion, and they will combine together, and you will see the T1 image is being dark. So the similar way you can detect some special DNA, because only there are two DNA fragments attached to Q and E, and the two fragments can only be combined by a special sequence of DNA. So if you put these two molecules into some tissue or into some solution, and if there are some special DNA, they will be combined together and you will see very low T1 image. But if there are no special DNA, and you will see the T1 image quite high. So this is special DNA sensor. And in the same way, if you bind it to some like a DNA chain or some protein chain, and this is actually DNA chain. This DNA chain are very sensitive to the pH value. If it's in acid condition, and the DNA chain will fold it. And so if you added to the Q and E at two ends, and they will be folded together from T1 image, you will see it's quite low signal. But if you put it, remove some acid and put it into the pH equals to 8, you make it to 8, and then the DNA chain will unfold it, and from the MRI you will see the high T1 image. The intensity is high. The same thing for Hg 2 plus, and this one with the Hg, and the molecule will fold it, and if you add EDTA, that will extract Hg to make a complex, and then it will be unfolded, and from the T1 signal that can be reflected in T1 signal. So here is one experiment on the mouse, that is to detect the MMP2 concentration. MMP2 is a very important biomarker for the malignant cancer. MMP2 is called the matrix metalproteinase. That means this MMP2 can cut the special amino acid sequence PLGVR. If you have this PLGVR, and this MMP2 will cut it into two parts. And for some, the PLGVR fragment actually contained in some fibers, especially in the extracellular matrix. So if the cancer cell can secrete this MMP2, and it will break the fibers, and then the cancer cell can migrate. So in this case, it is we call it a malignant cancer, because it can migrate to some other organs. But for some benign tumor, even though it is very big, but if the boundary is not broken by MMP2, and you just do the surgery, and the patient will have no too much danger because it's benign. So how to detect MMP2 is very important, and here the author gave a special, they call it MRET probe. The MRET probe has a special sequence that PRGVR in between, and on the two end quencher and enhancer. So you can inject this probe into the tumor. If the tumor contains MMP2, and then the sequence will be break into two parts, and then T1 image will show you high intensity, like here. In this mouse, there are some the tumor X grafted in this part, and the tumor contains some MMP2, and so the MRI image is bright. But here it's quite dark, because we not only inject the probe, but also inject some MMP2 inhibitor. That means there's no MMP2, and the signal T1 signal quite low. So here is another image. There are four kind of tumor cells injected to four X grafted to two mice, and because these two tumor cancer cell lines contain different concentration of MMP2, so from the image we can see the reactivity change, the difference. Actually, is linear dependent on the MMP2 concentration. So from MRI image, you can see the higher of the T1 image actually correspond to the higher of MMP2 concentration, and the relativity change is linear dependent on the MMP2 concentration. So this is the whole picture, and we know last year the Nobel Prize was given to the molecular machine, and currently the scientists can make different kind of like a nano car. We can make some like a nano switch that can open and set the neurons. We can also make some molecular Caesar, these kind of things. And we also try to use these kind of things like to kill some cancer cells. We try to use these things to like deliver drugs to special area, special organ. But this kind of machine you can inject it into your blood, into your body. But currently we lack the ability to detect where are they, where are the machines, and we also lack the technology to detect if the machines are working or not. So normally when the people do this experiment, they have to use microscopy. They cut the tissue and to see what happened, use the microscope. But MRI actually can provide you a tool that can see what happened in your body, especially the tissue is opaque. They can see what's inside, what happened inside. So since the Korean group give us this very good MRET tool, and we can combine this Q and E to the two end of the nano machine, and then we inject the nano machine to deliver drugs or to do some other things. And in this case, we can not only detect where are the machine, nano machine and molecular machine, we can also know if they are have some like reaction with different proteins or etc. Because if they do some uh, reaction and the molecular conformation will change, like the Q and the E distance will change, so we can see it from the T1 image. So I think this one is very good approach for our biology and especially for the medicine science.